Good afternoon. This is Earth History. This is our video lesson for Chapter 9. So Chapter 9, we are still in the Precambrian, but we're in the second half of the Precambrian, known as the Proterozoic. So if you remember from Chapter 8, that was the early part of the Precambrian, called the Archean, and that went from 4.57 billion years ago, beginning of our Earth and solar system, until 2.5 billion years ago. So Chapter 9 then is the second half of the Precambrian, known as Proterozoic, and this goes from 2.5 billion to 541 million years ago. Why do we make a break here at 2.5 billion? And the answer is that we see a change in the style of crustal evolution at this time. So many continents that formed in the Archean, and remember that continental material does not subduct, so once it forms, it's pretty much going to stay here. So Archean mini-continents allowed accretion on continental edges and formed larger continents, protocontinents, we might say. So rocks from the Proterozoic are, well, they're old, but they are generally unaltered or slightly metamorphosed, meaning that there's not really much folding going on within the continental interiors anyway. On the edges of the continents, that's where you're going to have accretion, and that's where you're going to have mountain building, and then you will deform those rocks. So you might remember from Chapter 8 video lesson, or what we did in class, if we do it in class, is that in the Archean we don't really have any passive margins. We just have a bunch of active margins. So we start to see passive margins appear in the Proterozoic. Remember that a passive margin is a coastline that does not lie on a plate boundary. So the east coast of the U.S. is a great example of a passive margin. What else do we start to see in the Proterozoic? Widespread deposition of sediments that would then form sedimentary rocks on our passive margins. I'm going to adjust the iris. I think it might be a little bright there. Maybe that's better. Okay, let's move on. And hopefully the light's not going to go out while we're filming, but of course it will. Okay. All right, nope, we got to adjust the iris a tiny bit more. Okay, there we go. All right, so other interesting things about the Proterozoic. Multicellular animals appeared. Eukaryotes appeared. So in the Archean, we basically only had the, what's the other one? Prokaryotes, and prokaryotes did not have a true nucleus. So eukaryotes are your more advanced cells, and they have a membrane-bound nucleus and organelles, and we see these cells appear for the first time in the Proterozoic. We also see the appearance of oxygen-dependent organisms. We're going to see that these protocontinents, old cratons, remember that craton just refers to the oldest part of a continent, and in particular the great craton is the part of that continent that's not really covered by a lot of sediments. Anyway, these protocontinents are going to grow along the margins. They really can only grow along the margins as other things smack into them, as you have subduction zones forming along the continental edges that are going to bring about some volcanism and mountain building. So Laurentia amassed during the Proterozoic. What is Laurentia? Well, it was a smaller supercontinent, meaning smaller than Pangaea, and before Laurasia, and it consisted of North America, Greenland, Northwest Scotland, and part of Scandinavia. Before this video lesson is over, we will have a short lesson on the supercontinents. I also have a handout for the supercontinents, and I need to go ahead and put it on my to-do list to make copies of that handout so I can be giving them out in class. Of course, as I'm filming this, we're not quite ready for our first exam, so I've got time to get those handouts printed. What else happened in the Proterozoic? Several orogenies, or mountain building events. In class today, at the end of Chapter 3, we put that term out there for the first time, orogeny, mountain building event. So we had several of these mountain building events occurring as we had these cratons, our protocontinents, suturing together Okay, meaning you got a couple of continents that smack up onto each other. Well, neither one is going to subduct, so they're just going to suture together. That means they, well, one accretes onto the other, and then they become one continent. What else happened? Well, you're also going to have, again, you'll have some oceanic material that's going to collide with these cratons, and you're going to form ocean-to-continent subduction zones. And what is that going to do? Well, that's going to build volcanic mountains. So you're going to have volcanic eruptions that add new material to the continent. And you're also going to have intrusions. Okay, so plutons and batholiths getting emplaced within the continent because of a subduction zone. So the volcanic eruptions, pluton emplacement, and island arcs and terrains and other protocontinents smacking up onto a continent, all of this means that our continents grow larger in the Proterozoic. So after Laurentia was assembled, and again Laurentia is before Laurasia, we had small cratons, again we might think of them as protocontinents or terrains, small cratons colliding along the eastern margin of Laurentia and the western margin of Laurentia, and then later along the southern margin. So the last step in building Laurentia was a very famous mountain building event called the Grenville Orogeny. It's very famous for sure amongst geologists in North Carolina and South Carolina. So there's this organization called the Carolina Geological Society, CGS, Carolina, sorry guys, it's been a long day, CGS, Carolina Geological Society, that's it. Okay, so in non-COVID times, once a year in the fall, geologists from North and South Carolina get together and they kind of rotate where they have the conference, and it needs to be set somewhere where you have some interesting geology to see or some interesting geologic history to see evidence for, and it also needs to be near a university and convention center that will host it. Anyway, I used to often go to the CGS weekend conferences, and there were a lot of field trips, and it was so much fun. And we see plenty of evidence for the Grenville Orogeny here in North Carolina, so it gets talked about a lot amongst our Carolina geologists. So the Grenville Orogeny, a famous mountain building event, and this happened along the eastern margin of Laurentia, and this occurred between 1.3 and 1 billion years ago. This was the final stage in building not only Laurentia, but Rodinia. At that point, by 1.3 to 1 billion years ago, you had almost all of Laurentia built, and then it was colliding with a couple other things to make Rodinia. Remember that Rodinia is the supercontinent before Pangaea. So at this time, by 1 billion years ago, we had about 75% of North America was present at that time. So the more recent 25% would get added on later through accretion and subduction on the eastern and western and southern margins. All right, moving on. You know what, I'm going to walk over here. Let's just go ahead and do it. Let me walk over here by the door since I'm off, so that the light will hopefully stay on and not go off. All right, so moving on with our notes. Okay, so something else interesting, other interesting things in the Proterozoic. So about 1.1 billion years ago, something happened in Laurentia. It was a period of extension or stretching. We called this the mid-continental rift. Now it's a failed rift, meaning that Laurentia attempted to split apart, but it was unable to. But it would leave behind normal faults and perhaps some volcanic activity. Mid-continental rift, not on your exam. It is on the notes here though, because it's interesting and I want to talk about it. Okay, snowball Earth. So there in purple, snowball Earth, also I believe is not on your exam, but I want to mention it because it was interesting. And at the end of the semester, well, after midterm at some point, I'm going to have you guys watch on your own time, of course, a 2-hour special by the BBC which is basically geologic history of the Earth in 2 hours, and they're going to talk about the snowball Earth. So between 900 and 600 million years ago, we had 4 episodes of very large-scale glaciation. Glaciers present even on continents that were clustered around the equator. As a matter of fact, most of the continents at this time were either lying across the equator or very close to it. And we had glaciation, not just at high elevations, but at low elevations. So that's why it's called snowball Earth, as in widespread glaciation. Would we want that to happen today? And the answer is, gosh, no. Okay, so why did snowball Earth happen? Well, it turns out that we had a lot of silicate minerals in our igneous rocks now, in particular, as our continents are growing and we're having more igneous rocks with those silicate minerals in them, they are subjected to weathering, chemical weathering. So chemical weathering of silicate minerals in igneous rocks takes carbon dioxide out of the atmosphere. And remember that carbon dioxide warms the atmosphere. So we had all this weathering, and we're pretty sure that is what caused the global temperature drops to make snowball Earth. Clearly, we're not in snowball Earth anymore. How did we get out of it? Volcanic outgassing. So some of the volcanic gases, well, carbon dioxide is one of them. Some of the volcanic gases, oxygen is another one, are actually greenhouse gases and helped us get out of snowball Earth. Okay, what else was interesting in the Proterozoic? Photosynthetic stromatolites. We saw them first appear back in the Archean, but they're very common by 2.3 billion years ago. Okay, we're getting ready to talk about the BIFs next. They're in purple, and this is very interesting. Okay, so we see evidence going back all the way to 2.5 billion years ago of starting to get increased levels of O2, atmospheric oxygen, in the atmosphere. And what's our evidence for it? Well, my favorite line of evidence are the banded iron formations, or BIFs for short. So what are these things? Well, they're basically layers of iron oxides like hematite or magnetite with chert, which is microcrystalline quartz, and they're just banded. Kind of alternating bands of chert and then an iron oxide and then chert and then an iron oxide and so on. And these banded iron formations were forming on the ocean floor. Now, they formed within a pretty narrow range of geologic time, 2.5 to 2 billion years ago. Okay, so why did they form? Well, prior to 2.5 years ago, say back in the Archean, atmospheric oxygen levels were low. Okay, and what happens when the oxygen levels are low? It means that iron oxides like magnetite or hematite are easily dissolved in seawater. So they're dissolved in the seawater and they're not growing out of the seawater. So we start to see oxygen levels increase at 2.5 billion, and what this did is when you now have more atmospheric oxygen in the atmosphere but also in the oceans, you now have an oxidizing state, and this allowed for iron to grow or precipitate or grow out of the seawater on the ocean floors in the form of those BIFs, banded iron formations. So we know that we were increasing oxygen levels from 2.5 to 2 billion years ago. Another line of evidence for increased oxygen happened about 1.8 billion years ago. We see sedimentary red beds appear. So they're sedimentary rocks and they're going to have a reddish color. That's why they're called red beds. And basically they are sandstone and shale, which can be interbedded. And you tend to have an iron oxide cement, so like a hematite, for example. And of course, an iron oxide, the presence of iron oxide tells you that you've had oxidation, and that is further evidence of increased oxygen. So a little snippet about life of the Proterozoic. Stromatolites became really common, again, after about 2.3 billion years ago. Again, our eukaryotes, our more advanced cells, they appear and become common. Our oldest eukaryote cell is at about 1.26 billion years ago. So again, multicellular organisms will appear and become common. So the Ediacaran fauna, that last snippet of notes here on this board, The Ediacaran fauna is a very important fossil find. So first discovered in the Ediacara Hills in, I believe it's Australia. And this was such an excellent fossil find. So these organisms lived between 635 and 541 million years ago. And our first real animals are included in the Ediacaran fauna. So there'll be a little snippet of the Ediacaran fauna in your e-text and also in the PowerPoints. So yes, we had algae. Of course, we still have algae today. But we also started to see soft-bodied organisms. Again, actual true animals appear in the Ediacaran realm. All right, we are going to move and do our last bit of notes, but once again, I will walk over here towards the door to make sure that the light doesn't go off. And then our last bit of notes for this chapter are the supercontinents. So again, I do have a handout of supercontinents that I'm going to print and give you guys. Okay, that might be a little too much glare. Let's move around a little bit. But I still want them in this video lesson. It's important. Okay, so this is your rundown about supercontinents. All of them. Yeah, I guess we're kind of going in order here of time. Okay, so we will begin with Laurentia. Yes, we talked about Laurasia back when we did Chapter 3 in Plate Tectonics. But Laurentia came before Laurasia. And we're going to see that Laurasia will form from Laurentia and some other things. But let's go all the way back to 3 billion years ago. So from 3 to 1 billion years ago, we had a smaller supercontinent forming called Laurentia. This consisted of North America, Greenland, Northwest Scotland, part of Scandinavia. And again, the last stage in building Laurentia was the Grenville orogeny that we see evidence of here in North Carolina in the mountains, if you know where to look. Grenville orogeny was between 1.3 and 1 billion years ago. That's included as part of Laurentia. Okay, but Rodinia, remember from Chapter 3, Rodinia was the supercontinent before Pangaea. Okay, so this Grenville orogeny, again, was not only the last step in building Laurentia, but other things had accreted onto Laurentia. We didn't have quite as much continental material back then as we do now. But that Grenville orogeny was also the last step in building Rodinia, which was our supercontinent before Pangaea. So Rodinia started breaking apart about 750 million years ago. Okay, so Pangaea, that's our one here down on the bottom left. Pangaea is actually not on your exam. I forgot to write that down, but I'm telling you. So Pangaea briefly existed for a couple 100 million years, no, 100 million years, sorry. And what happened is that Rodinia's pieces, some of them briefly got together and formed Pangaea, which lasted from 650 to 550 million years ago. But again, Pangaea, not on your exam. All the other ones are fair game for your exam. Which exam? I guess this is the second exam? Okay, yeah, again, light glare, is that better? I think that's better. Okay, Laurasia is next. Laurasia is a term we have heard before. We were very simple in describing Laurasia back in Chapter 3, and we said it was the northern continents clustered together. Now we'll go into more detail. So Laurasia existed from about 428 million years ago during the Silurian to part of the Cretaceous running from 145 to 66 million years ago. So what happened here is that you begin with Laurentia, and then you add Baltica and Avalonia colliding with Laurentia, and that made Laurasia. Now Laurasia will eventually collide with Gondwana to form Pangaea. But first let's talk about Gondwana. I think I mentioned before, in Chapter 3, Plate Tectonics, all we said about Gondwana, it was the southern continents together. And I might have mentioned then that Gondwana lived a long time. Okay, so Gondwana, southern continents together, existed from roughly 522 to 200 million years ago. And then eventually, roughly 250 million years ago, Laurasia and Gondwana are going to come together and form, gosh, this light glare is terrible, and form Pangaea. So Pangaea, our most recent of the large supercontinents, fully built by 250 million years ago. So that means the Appalachian Mountains were fully built by 250 million years ago. Again, this is Laurasia and Gondwana come together, and it began to split about 200 million years ago. Now, sometimes geologists like to discuss something called the Tethys Sea. So the Tethys Sea was this decent-sized sea that was stuck between Laurasia and Gondwana. And as Laurasia and Gondwana came together, we lost a good bit of the Tethys Sea. But there's a small portion of it that's left. And today it is known as the Mediterranean Sea. And today it is over there in, I'm turning to look back at the continent. It's over there in between Africa and Eurasia. So the Mediterranean Sea is the remnants of the ancient Tethys Sea. So where will you find the absolute oldest oceanic crust, going up to 200 million years? That's going to be in the Mediterranean Sea, which is the remnants of the ancient Tethys Sea. So we did not lose all of the Tethys Sea. And I think that is it for Chapter 9 video lesson.